Hello everyone, my name is Mwathi, and today I'll be presenting on the Tacoma Narrows Bridge collapse, lessons in engineering and aerodynamics. Introduction. The Tacoma Narrows Bridge, built in 1940, connects Tacoma and the Kitsap Peninsula in Washington State. This bridge was nicknamed the Galloping Gear, becoming infamous for its dramatic oscillations and collapse. This event is considered one of the most significant engineering failures in history. Today, we'll explore the causes of the collapse and its lasting impact on bridge engineering. To the right side of the slide is an image of the bridge on opening day. Background. The bridge, the bridge was a marvel of modern engineering at the time. Its span of 2,800 feet made it the third largest suspension bridge in the world. It was designed to be sleek and aesthetically pleasing. It was a symbol of innovation. However, the design prioritized aesthetics over functionality, particularly wind resistance. Its nickname, Galloping Gear, came from the unusual lateral movements uh, that were observed even before the collapse of the bridge. The collapse. On November 7th, 1940, just 4 months after the bridge opened, the collapse occurred. Strong 40-mile-per-hour winds created oscillations that matched the bridge's natural frequency, a amplifying the vibrations. A- As the resonance, as the res as the resonance increased, the bridge's deck twisted violently and eventually disintegrated. Remarkably, no human lives were lost, though a dog did perish. The entire incident was captured on film, and this footage shocked engineers and the public alike, highlighting the catastrophic consequences of design oversight. A major key flaw, a major key flaw of the Tacoma of the bridge itself was lack of adequate wind resistance. Flexible design of the bridge was not equipped with stiffening trusses to counteract the forces of the wind. In addition, no wind tunnel testing was conducted during the design phase, which which would have highlighted the potential issues. This lack of consideration for aerodynamics ultimately played a key role in the collapse. On the right side of the presentation, you can see the image of the main part of the bridge falling into the strait. Engineering analysis. The collapse the collapse was caused by resonance. When the frequency of the wind matched the natural frequency of the bridge, this this led this led to torsional oscillations that amplified over time. The design's flexibility, lack of stiffening trusses, and the absence of wind tunnel testing allowed for the oscillations to grow uncontrollably. This incident underscored the importance of considering aerodynamics in the design of large structures, a lesson that would a lesson that would reshape engineering practices today. As you can see below this presentation, an image of a fragment of the collapsed bridge from the day of the collapse. Aftermath and lessons, as well as lessons learned. In the aftermath of the collapse, the bridge was rebuilt in 1950 with a more rigid design, including additional trusses for better wind resistance. Wind tunnel testing became a became a standard practice for bridge designs going forward. As well as the collapse also contributed to the development of aeroelasticity, a specialized field which focuses on the interaction between wind and structures. Today's event is being studied in engineering education worldwide as a critical case study in design flaws and failure analysis. As you can see to my right is images of the original bridge in the 1940s, and on the bottom, the rebuilt bridge in the 1950s. In summary, some of our key takeaways can be aesthetic innovation must be balanced with safety, as engineers must prioritize functionality alongside beauty. Rigorous testing and analysis are crucial in preventing catastrophic failures. And thirdly, it and thirdly, Interdisciplinary approaches, in this case, combining engineering and aerodynamics, are essential for addressing modern changes. The following is are the following are my references I used for this presentation. Thank you.